Okay, thank you. So welcome everyone. As you have already said, I will be the first presenter and I'm representing Hungary. Currently, I'm a PhD student and I'm just finishing my 4th year of studies. My supervisor is Balázs Csanácsai and we are working together in the field of statistics, and our main field is constructing confidence bands. And as in these introduction slides, I will hopefully can give some brief introduction to what is our aim and what are we assuming and so forth and so on. So the problem setting, as you can see, is quite standard. We are coming from a finite sample of IID random pairs, and we assume that they have an unknown joint distribution. And the problem setting comes in this form that we have the data with some measurement noise, which is denoted by this epsilon variable. We assuming that the expected value of this noise is 0, and the dimension of the data will be denoted with this small n as usual. So what is our aim with this data? Formally speaking, we are looking for to construct a confidence band for this original regression function, which we denote with f star. And this confidence band basically means that we want to guarantee that every input points are included in this confidence band. So the formal reliability, which can be seen here, is basically meaning that we want to include every single input points of this function in this confidence band with a given risk probability. So this alpha parameter, which we can choose between 0 and 1, is basically decided before the task, or whatever we want to achieve. So if we plug in 0.1, then we achieve 90% reliability. And the aim is to construct such an I function which can guarantee this reliability for the regression function. So probably many of you have heard about the Gaussian regression, which is the most standard solution to this problem. I have brought some plots which provide solution for several problems. One is a noise-free setting and the other is a noisy setting. And yeah, this is a very standard solution, but the issue with it that it has pretty strict assumptions regarding the data set. So it is required that the data has a jointly Gaussian distribution. And in some cases, this can prove to be pretty unrealistic. So this method in particular is not distribution free. And our aim was to construct an algorithm or a method that can be guaranteed for any distribution. So we shouldn't have to make any assumptions about the background data. So here I listed the main assumptions about the data set, the regression function, and everything behind it. The first, with this A0 assumption, is what I already showed. It is the standard IID assumption. The second assumption is basically what are we assuming from the noise, which is denoted by this epsilon variable. We are assuming that they are independent from the inputs. And this compact matrix group, which I listed here, is a pretty mild assumption. I prepared a slide for the next one, which basically describes what this assumption means. But it is a mild assumption, and many standard distributions satisfy this A1 assumption. And the last two assumptions are basically regarding the regression function. So the A2 assumption means that the inputs, so the X set is assumed to have a priori distribution, and we assume that this distribution is known. And the second or the last assumption basically means that the F star regression function comes from a Bailey-Wiener space. And I also prepared a slide about this Bailey-Wiener space too, to describe what this essentially means. And these inequality constraints are basically some regularity assumptions only. So about this distribution invariance, which I mentioned for the noise, is basically a standard assumption, and many distributions satisfy it. I listed also two basically trivial examples. So if the noise is exchangeable, for example, if I have an IID data, then this assumption is already fulfilled. But the question arises then, why do we even have to assume this? Is if we maybe have more information about the noise. So if one knows that the noise behind the data is symmetric, then we can use a more sophisticated algorithm for the problem. But basically, the IID assumption already satisfies this problem. And I also prepared a slide for the Paley-Wiener space, which is basically our work frame. This is a reproducing kernel Hilbert space, which could seem quite unusual at first sight, but the main motivation behind it that we limit the frequencies of the target function. So we basically work with band-limited functions. That means that the function can't change its value too much on a small interval. So it can't be arbitrarily large in a really low section. This space is used probably in signal processing and many fields, and it is a quite standard assumption to work in this space. And here, because it's a reproducing kernel Hilbert space, I also listed its reproducing kernel, which is given by this formula. So this was the description of the main task and the main assumptions. And here I will try to give a brief description of the method. The first case will be presented similarly to the Gaussian, which I showed previously, to the noiseless outputs case. So we are working with a simplified problem here. We assume that the true regression function can be observed perfectly at the inputs, so that epsilon noise, which was assumed to be in the problem, is basically non-existent in this case. And we try to solve the problem. So we try to provide confidence bands in this noise-free outputs case. And here I will take advantage of the reproducing kernel property, because we are working in this Paley-Wiener space, which I will just now refer to this as this capital H symbol. And I listed this function, which will play a core part in providing our solution. So since we are in this space, we can construct this f bar function, which basically interpolates these noise-free outputs. So as you can see, for every single x inputs, it interpolates these points perfectly. And why is this function special? Because we chose it in the way that it has the minimal norm. And this function is given in the following form, as I listed here. It is basically given by some weights and the reproducing kernel, as I listed by the formula in the previous slides. And it takes on this following form. And we will use this function to provide an upper bound for the norm of the unknown regression function. So this function will help us to create some bounds. And how do we do that? Well, basically, we take the idea that we just take some random x0 and y0 pair, and we just extend this interpolation function with this new pair of points. And we will construct the function in the way that basically the formulas are the same as before, just extended by this x0 and y0 point. And since we are in a reproducing kernel Hilbert space, the norm of this interpolant can be obtained in the formula as given in this last line, which will be quite useful when we need to provide the upper bound. So this was the core idea. And basically, there are many equations here. I prepared the slide mostly with words and ideas to give a short idea what are we doing here. So we just take a candidate pair from our distribution, and we calculate the norm of that interpolation function extended with this candidate pair. And what we do after we calculated this norm is we check if that norm is less than equal to a calculated upper bound. And if it's less, then we basically include that candidate pair in our confidence band. But if the case is that it's greater than our calculated upper band, then we do not include that in our confidence band. So the question arises that how do we provide an upper bound for this norm of the regression function, and we also need to provide a method how to decide the endpoints of the confidence interval. So since I don't have an infinite amount of time, so I can't go into details about how this norm estimation is calculated, but I can listed here the main formula. So basically denoted by this kappa provides us a upper bound for the noise-free outputs case, and with a chosen risk probability, we can guarantee that the norm of this regression function will be less or equal than this upper bound with a given probability. And how do we obtain the confidence intervals? So basically, we arrive at some optimization problems. So once we have a candidate pair, we are looking for a minimal and a maximal value where the interpolation function basically lies below this upper bound that we calculate. And this arrives at two convex optimization problems. So we have to solve a minimizing and a maximizing problem. They provide the lower and the upper part of this confidence band. And in this special case where the outputs are noise-free, these two convex optimization problems are also they can also be reduced to analytical problems, so that we don't have to solve convex optimization problems every time. In this noise-free case, they are pretty easy to calculate. And next to all these equations and optimization problems, before stating what I will state the main theorem. So basically, this reliability is guaranteed in the noise-free case with this risk probability if the assumptions are fulfilled and if the outputs are noise-free. And we have seen a lot of equations, but hopefully some figures can also help to understand what is the main concept of our method. So in this noise-free case, I provided two constructions, one with a 50 and one with a 90% risk probability. And you can see that in our case, both were successful, as a true function, which is denoted by this blue line, lies both in both confidence bands. And you can see that the 50% confidence bands is a bit more informative in this case. And you can also probably see that near the outputs, it is pretty smart, but when is a big gap, it can be it can turn pretty hard when there are no inputs in a larger interval. And I will also try to provide the construction of the noisy case in a timely fashion. So in this case, we no longer assume that there are no noise affecting the outputs. And it makes our case a bit harder since we can no longer observe these points perfectly. What we can do instead is use some methods to guarantee that the observations lie in some confidence ellipsoids for those inputs and work with those. So basically, in the noisy case, we have one more problem because one more uncertainty constraint comes in the picture. Here we denoted it with beta. So there is one more uncertainty in the problem if these inputs lie in the actual confidence ellipsoids. And one of the methods that we used to provide such ellipsoid was a gradient perturbation methods. Also, I can't really go in the details here either. And the problem is actually similar. So once again, we have to provide an upper bound for the norm of the function. And we arrive at the following optimization problem. The form of it is quite similar, but the problem that arises here that the convex, it is not actually convex. So this problem that we constructed here couldn't be solved. So, but luckily, thanks to the strong duality, we could use the dual, the Lagrangian dual problem instead. And in this slide, an equivalent form of this dual problem is presented. Can't really go into the details about these constraints here, but luckily this dual problem is convex, and the optimal solution, which is given here, also provides us a nice upper bound for this norm of the regression function. It is given by a similar formula than before, and we can also state a lemma similar to the noise-free case. As you can see here, the statement is quite similar, only that one more source of uncertainty comes in the picture. So the alpha comes from actually the upper bound uncertainty, and this beta uncertainty comes from the confidence ellipsoids for the inputs. So there are two factors in the noisy case. And how do we construct the ellipsoids in the noisy case? Basically, since this ellipsoid guarantees the incursion of the inputs in the following way, we can construct a convex problem similarly to the noise-free case. We once again solve a minimization problem and a maximization problem for a query or a candidate input-output pair, and we check if the norm of this interpolant function is below or estimated norm, and the one more factor, which is here, that these decision variables have to lie within this confidence ellipsoid. And once again, basically the minimizing problem gives the lower part of the confidence band, and the maximization problem, that solution provides the upper part of the confidence band. And we can state a similar theorem for the noisy output case too. Once our assumptions are satisfied and these risk probabilities are chosen however the user likes. So some core examples would be if I want to guarantee a 90% incursion or a 90% reliability, then I can choose, for example, both alpha and beta to 95%, or I can choose however we like. Basically, we subtract both from one because we can use the union bounds, and this inequality is basically taking a worst case scenario for the reliability. And once again, I prepared some figures to demonstrate the method. In this first case, the noises behind the outputs follow the Laplace distribution. And as you can see, both the 50 and the 90% confidence bands were successful in the sense that the original function, which is once again denoted with this blue line, is included in both confidence bands. But as you can see that once noise comes in the picture, this problem is not really trivial, in the sense that once I only see the noisy data, it's quite hard to estimate how the regression function actually looks like. And in the following slide, I prepared a similar problem, but also a strange one, since we worked with exponential distribution in the noise. And what's interesting about this figure, that the noise is non-symmetric in this case. Hopefully it is visible that some of the data are spreading more upwards than towards the negative side. And as you can see, in this case, the method also proves successful. So both the 50 and the 90% confidence bands include this original regression function. And hopefully these figures helped to give some clarification or some picture about how these methods work. And just briefly, hopefully I'm still in time, I just want to conclude basically what the method provides. And I also listed the related publications that we worked on so far. So basically the core things that we can guarantee about this method, that is distribution free. So we didn't assume anything about the f star function, except that it lies in this band limited Pelley-Wiener framework, but we didn't have to assume any distribution about the noise. The method is also non-asymptotic and non-parametric, and basically it's also simultaneous because it's not just for some inputs or some observation, but it provides confidence bands for the entire regression functions. And similarly to the Gaussian figures, I first presented the noise-free case when the outputs are observed perfectly, and then I went to the extended noisy version. And the method basically comes from two main ideas. First, we calculate an upper bound for the norm, and then with this norm, we can generate the confidence band for a certain candidate input-output pair, and we just basically test whether the function satisfies that constraint that we give for the norm. And finally, I just listed here the related publications. Hopefully I was in time. Thank you for the attention. And I don't know if questions arises, or where should I look for questions, in the chat, or I just answer them here? Thank you.
Andrei, you have a question?
Thank you. This is also to stimulate, hopefully, questions in further. So on one slide that you had with the graph, I noted some, at the start, quite disparities between the confidence bands. I think that on certain cases they were very wide and on certain very tight. Is there any explanation for this? I think
can you specify that it was these or the noise-free case?
It was at the beginning, about 6-7 slides, one of the first cases.
Maybe this one.
If you share it again.
Is it not shared?
No, I don't see it.
Oh, I didn't quit it, but let me share again. I just jumped there. Can you see it now, maybe?
Yes, it's precisely
it was this figure, right? So you basically ask why is it so tight in one part and so wide on the other part?
Why the differences? Yes.
Basically, as you can see, maybe between these 0.8 and 0.4 section, it didn't receive any information. So there are basically no inputs between these big intervals. And as you can see in parts where inputs are fairly next to each other, it is pretty smart. So in this noise-free case, I brought this figure because if I wrote something similar to the noisy case, it would be basically just lines. So the noise-free case is pretty easy to solve in that case. I wouldn't say it's trivial, but once I have so many inputs in a small interval, basically I would just show lines and not confidence bands. So if I took something like this, in the noisy case, I wouldn't be able to show such bands. I would just show basically lines which almost perfectly take on the value of the original function. But probably this is more informative. This is like 10 inputs. So 10 is a pretty small number when one thinks about the data. But the main explanation is that if there are no inputs or no information in a bigger interval, then it becomes quite uncertain about that constraints.
Okay.
Hopefully that answers it.
More than enough, yes.
Thank you.
Thank you.